Hello and welcome back to another lecture from organic chemistry. In last lecture, we've been talking about the electrocyclic reaction, and we said it depends to the condition, whether it's a thermal or photochemical. We can have a different type of rotation. Conrotatory, they will be in the rotating same direction, or disrotatory, the two groups that will rotate opposite of each other. But the thing that we have to be careful about it is going to be number of pi electrons. And you can go with these two formula. You can go for n and for here 4 pi electrons, or you can use actually 4n plus 2 to predict how many pi electrons you are dealing with, and just simply put n say 1 2 and go on and see how many pi electrons you get. If you get 6, then you're dealing with you're dealing with 6 pi electrons. Or for example, if you get 10 electrons, then I'm going to say this is the pathway that you have to follow. In case of thermal, it will be this rotatory, and if you're dealing with photochemical, it will be conrotatory. And I can use the same thing for n again, say n1 2, and if I put 2, I get 8 electrons. So I'm going to say that's going to follow actually the first pathway, and it depends on the condition. If it's thermal, it will be conrotatory, and if it's photo, it will be disrotatory. Okay. Now, I want to switch to the last class of pericyclic reaction, which is sigma-tropic rearrangement. And again, this is a pericyclic reaction. One sigma bond will be technically replaced by another one. So we are not, replacing a pi bond by a sigma. Just simply we change the position of the sigma bond. I want to know, how to label them and get some, technically know some, terms about how to label a sigma-tropic rearrangement. Let's start with this one. First of all, we are dealing with sigma rearrangement. So we are taking 1 sigma plus 2 pi electrons, and that means we are dealing with 1 multiply for sigma. We're going to use 2 electrons, so multiply 2 electrons for any pi electrons. Again, we are any pi bond. We're going to use 2 electrons. So I'm going to say plus 2 multiply 2. That's going to give me 6 electrons. 6 electrons. Okay, because I got 6 electrons, I can say this one is following this formula, 4n plus 2. Okay, and if n is equal 1, in that case, I go 4 multiply 1 plus 2. That's going to give me 6 electrons. So I'm going to say this reaction is building technically or dealing with aromatic transition state, or the pathway that is going through it. It will go through it will go through a way that's going to generate aromatic transition state. And because it's aromatic, the transition state is going to have lower activation energy. So aromatic TS, or transition state, will end to lower activation energy. And this is the reason the reaction is going to happen technically. So one driving force for it is having cyclic and also aromatic transition state. Now, label the bond that you are breaking technically. So this is the bond that we are breaking, and now from both sides of that bond, start counting. You say 1, 2, 3, and then again here 1, 2, 3. Okay, and as you see, the sigma bond from the left side moved to the right side. Okay, how many carbons we rearranged? Technically, I can say 3 at the top and 3 at the bottom. So I'm going to say this rearrangement is going to be 3 and 3. And what's the meaning of 3? The first 3 is telling you how many technically, from the bond that you broke, how many carbons or how many atoms, not just carbon, how many atoms, you moved. And also in the bottom one, we moved, 3 atoms. So I'm going to say 3 and 3. Question is it possible to have rearrangement other than 3 and 3? And let's see how we can get other rearrangement. And one is going to be 1 and 5 sigma-tropic rearrangement. And because it's a sigma rearrangement, and we need to find a sigma bond. And the sigma bond is going to be this, the one between hydrogen and a carbon. So I'm going to say hydrogen, it will be number 1. And other side of the sigma bond, I have carbon, that's going to be number 1. And then I say 2, 3, 4, 5. And the way it's going to move, and we're going to take number 1, and hydrogen, we will give it to carbon number 5. And so technically, we will have an intermediate like this, while hydrogen is somewhere in the middle, and hydrogen is attached to both carbon number 1 and 5, and we're going to get resonance there. Okay, so as you see, I have resonance, and because I have resonance, the system is going to be stable. Again, we have 2 pi bonds, and 1 sigma bond is involved, so totally have 6 electrons, and that's following 4 n plus 2. And so I'm going to say 4 multiply 1 plus 2, that's going to give me 6 electrons. So this system, it will be aromatic, and because it's aromatic, the transition state, it will have lower activation energy. Now, after that one, we're going to rearrange this molecule in order to get such a structure. The methyl group attached to carbon number 4, so we will leave it there. And now, as you see here, okay, the double bond is supposed to move between 4 and 3. Let me again label them. This is number 5, this one 4, 3, 2, 1. So we're going to have a double bond there, and also a double bond between number 1 and 2. Where's hydrogen? Hydrogen is going to show up on carbon number 5. And so hydrogen from the left, or carbon number 1, move to the right side, and that's that type of rearrangement. We call it 1 and 5 rearrangement. 1 and 5 sigmatropic rearrangement. Okay, and I have to say this one in all the cases, like all the time, like it depends, like what actually what's the condition that you're using, and what's the temperature and the substituent you have on the molecule. You might get equilibrium, or maybe you will be dealing with a condition that really the efficiency is not high, and you will have a plenty unreacted starting compound. And so don't be surprised if you, for some reaction, if you see an equilibrium between the starting compound and the final product. Okay, now as I said, the sigmatropic rearrangement is not that favored, and you need to use some techniques actually to push the reaction to the final product, or to increase the efficiency. One way is to maybe play with the size of the ring. Start with a compound that it has huge strength, and then in the final product it gets bigger ring. In that case, I'm going to say the reaction, it will be faster. For example, let's say if you put in here and a ring there, that ring is going to have huge strain, so it will be looking for a reason to get rid of this bond, and then the reaction is going to be really one way. Okay, but let's practice this reaction. It's a sigmatropic reaction, a sigmatropic rearrangement, and in this case, all the atoms that they are involved, they will be carbon atoms, and we have a specific name for it, and we call it rearrangement. Okay, again, we have 6 atoms, and all are carbon. And so what do I get? The product that I will get. Okay, let's highlight the bond that we are dealing with. That's a sigma bond that we are dealing with. We're going to start labeling it. So I go 1, 2, 3, and here I go 1, 2, 3. Okay, so what do I get? And I will get structure like this. So I'm going to have a double bond here. Okay, and that's going to turn sigma, and here we will have a double bond there. Okay, and what else? We have a methyl group, which is this position. Okay, now let's follow. Okay, the position of the double bond, and see whether really we favored it. There's any driving force to move the reaction from left to the right side. Okay, and I have a double bond here. It has 2 substituents, and this double bond, it has 1 substituent. Now let's compare them with the starting compound. Starting compound, it has only 1 substituent, which is in carbon number 1 attached to carbon number 2. How about here? Again, only 1 substituent. Okay, you might say this one did not change. Okay, yes, those 2 really the same, and only 1 substituent. But how about this bond? That bond, it has 2 substituents. Well, that one, it has only 1 substituent. And remember, we said if we get more substituent attached to the double bond system, it will be more stable. And if I remember correctly, we called this one the product. Okay. The double bond, the alkene with the alkene that has more substituent, we call it the Zaitsev product. Okay. Now, because the reaction is favoring to the right side, so I'm going to draw the arrow to the right side and longer than the return one. And so I'm going to say this reaction is favoring the product rather than the starting compound. And in this case, I believe we get 85% on the right side, and this one just 15%. Okay, so the Cope rearrangement is a sigmatropic rearrangement, but we are using six carbon atoms. And label, if you want to label, you will call it 3 and 3. Because number of the carbon that are involved, the number of atoms that they're involved on each side of the sigma equal to 3. you.